In this lab, we worked to construct an electric train using 4 items: a pair of magnets, a AAA battery, an uncoated copper wire, and a plastic tube. So how is this done? First, we must familiarize ourselves with electromagnets. When a battery is placed inside a conductive coil, it produces a closed circuit between the 2 magnets, causing a current to flow. As the current flows through the conductive copper wire, a magnetic field is generated. This magnetic field interacts with the one generated by the magnets in a manner that repels the magnets on one end and attracts the magnet on the other. A solenoid was created in this lab, which was constructed of uncoated copper wire coiled into a helix, which serves as a good conductor. It was done in a clockwise direction, which equates to a magnetic field likewise generated in a clockwise direction, which is shown by Maxwell's right-handed corkscrew rule. When the magnetic field is passed along the wire, it creates a uniform magnetic field through the center of the solenoid. These magnetic field lines can be seen in blue in this diagram here. This uniform magnetic field running through the center of the wire is denoted V. If you want to determine the strength of the magnetic field, it can be quantified using this equation. I here indicates current. Also, the strength of a magnetic field is proportional to the number of turns of wire and the strength of the current. The north and south poles of the conductor is determined by the direction of the electrical current flowing through the conductor. Ampe's right-hand rule illustrates this. If one were to grab the coil with their right hand, with their fingers curling in the direction of the current flow, the direction your thumb points is defined as the south pole, as the coil is wound in a clockwise direction. If wound anti-clockwise, your thumb would likewise face the north pole. The thing about electric fields is that they always have an associated magnetic field, regardless of the material it flows in. This is a key aspect of electromagnetism, which is defined by Ampe's law. When magnets are attached to either side of the battery and resting on uncoated copper wire, a local circuit is created along the length of the battery. The magnetic field generated by the coil interacts with the magnets, which causes a force upon the magnet inside the field. The current in the solenoid comes from the battery, flows through the magnets and onto the uncoated surface of copper wire. This circuit is created through the positive battery terminal into the magnet, through the solenoid, and back into the magnet on the negative battery terminal. This local circuit generates a current that creates a magnetic field within the solenoid. As you can see from this diagram here, the magnet on the right is repelled to the right and the magnet on the left is attracted to the right by the field within the solenoid. Together, these forces push the battery along the solenoid. Here is a demonstration of this force, considering the orientation of the magnets, the battery, and the handedness of the coil. The magnet's attachment on either side of the battery was key in allowing the magnetic poles of the magnet to simultaneously be attracted and repulsed in and out of the local circuit. This is the force that allowed the movement of the electric train. Additionally, as the train moves, it creates a new localized circuit that perpetuates motion. The magnets were also oriented in a manner that had the same poles facing one another. This allowed force in the same direction to be combined. Like-facing poles would result in a cancellation of forces, meaning the train will not move. Additionally, if magnets and their respective dipoles were flipped, the force will reverse direction and the battery will move in the opposite direction through the solenoid. Flipping the battery or handedness of the coil will also change the direction of current. There were no real complications in the conduction of this practical. However, as the strength of the magnetic field is proportional to the number of turns of wire per unit length, in addition to the strength of the current passing through, this could be quantified in the future, knowing that the voltage of a AAA battery is 1.5 volts, and measuring the length of the coil, which would give us the values to tabulate magnetic force, in case we were curious. In conclusion, the construction of this electric train allowed the illustration of the most basic principles of electromagnetism and engineering.